So hi and welcome everybody. Welcome back to the lecture of to the second lecture on wireless security. In the first part, we talked about the key security requirements and how to meet them in wireless networks. We specifically talked about authentication, confidentiality, integrity, availability, and privacy. And we mentioned that those are very critical requirements in any network, whether it's wireless or wired. And we briefly explained how we can achieve those requirements using encryption methods. Some of the encryption methods that are available on the in the standards and accepted worldwide, whether on the internet or in messaging, in voice communication softwares or video communication softwares, and so on and so forth. So what we are going to do now is explain these encryption methods and the differences between them, and how strong they are, and what are their advantages and disadvantages, and what can we do to improve them more. So now we summarize the encryption methods into three categories. We said the first category is asymmetric encryption, the second is symmetric encryption, the third is hash encryption. So the asymmetric encryption includes private key and public key. So if you want to send information to your friend should share with you his public key, and you use this public key to encrypt a message to your friend. Then your friend will use his private key to decrypt what you have sent him. If your friend wants to send you something, he has to get your public key and encrypt the message with the public key, with your public key, and then you, with your own private key, you can decrypt the message. If you want to sign something and authenticate that you are the owner of the message or something like this, then you use digital signature. This is asymmetric encryption. So in asymmetric encryption, you use two different types of keys, private and public. An example of this is the HTTPS that you use while you are browsing on the internet. And I showed you how to see the length of the key, which encryption algorithm is used, and the key itself, and the bits, and who's issuing that certificate, and what's the length of the key, and what digital signature you are using, and all these details. Plus, we also talked about symmetric encryption. Symmetric encryption, you use only one single key at both the transmitter and receiver. Now, what's the difficulty in symmetric keys? The difficulty is in sharing this key securely between the transmitter and receiver. We want to make sure that both of them have the same exact key, and this key should not be known to anybody else on earth except the parties who are communicating with each other. Nobody else. Just the guys who are talking with each other, they should know the key. Now, this method causes less delay and less resource consumption compared to asymmetric key encryption. Like asymmetric encryption is widely used on the web, but it's less efficient, and it can cause delay and consume more resources more than needed usually. So the third type is hash function, has a hash encryption, where you have a one-way hash function that takes your message and encrypts it. And in this case, you don't use usually any keys, and this is used to protect your communication and to protect its integrity. The ECC is another, is ECC, RSA, DSA, all of those are encryption methods that can be listed under the asymmetric encryption approach. In ECC, they call it elliptic curve cryptography. RSA stands for the names of the inventors of the encryption method, and each one of them can have different keys with different lengths and different security levels. So the way that ECC is implemented is described in this figure. where you have your message. Bob wants to talk to Alice. You have the message, you hash to point on elliptic curve, then you have the private key, you multiply it by this hashed point on the elliptic curve, and you get a signature. This signature, you multiply it by another point on the elliptic curve, and you get the output. You get something like your private key multiplied by the message multiplied by the point on the elliptic curve. The private key can also be used with the public key and the point on elliptic curve to send your message to the intended user. Like you sign it and let him know that you are the authentic user, that you are talking with him. Now here in the red box here on the right hand side, I'm putting a note here, homework. I want you to just check this link and see how to implement ECC in Python. You have the code here. I want you to go over the code and check how this algorithm really works. So I'm not expecting you to go try to know all the details of it, but at least you know how to code it and you know how it works, and that you can take this code and implement it in your machine and make this method works. So basically here you have, if we were to summarize them, you have the sender, you have the receiver, you have the key generation process where you have public key, private key. The private key is used for in the signing algorithm for authentication purposes and for certification, while the public key is sent to anybody on the internet who wants to talk to you. And this is basically the approach that's used in cryptocurrency and Bitcoin, where you have digital signature as well as asymmetric cryptography, private and public key. So since we have talked about cryptography in blockchain and Bitcoin, so what are the exact algorithms that are used in Bitcoin and cryptography? So Bitcoin adopts digital signatures, as I just mentioned before, to sign with the private key. And it uses the same technique that's used in elliptic curve. Encryption used in elliptic curves, ECC basically, that I showed you on a website like this, a researcher store, where you click and you see the link of the ECC and the strength of the encryption method. And the name of the algorithm in this case, since it combines both asymmetric public key encryption and digital signature, the name of the algorithm becomes ECDSA, elliptic curve digital signature algorithm with elliptic curve, and this is the type of the elliptic curve. For both encryption and digital signature, each user of the system generates a pair of keys. This is definite, this is a prerequisite. To start a secure communication, you need to have 2 pairs of keys. And usually the user who has the certificate, the private key never shared with anybody, only the public key. And the public key is then translated to the wallet address that you can use to send money and receive money. The public and the private keys are mathematically related. Think of them like a full complete structure, and you separated this unique structure, this singular structure, into 2 parts. And whatever you do with you use half of this single unique structure to encrypt, and to decrypt and remove the effect of the first part, you need to use the second part, which is the public key, to get the original message. So both keys are mathematically related, and it's computationally infeasible to derive the private key from the public key. Let's say I gave you a public key, and I tell you find the private key. It's so difficult mathematically, and it would take years from you using even a supercomputer sometimes, because it depends on the computational complexity of the reverse function that you are using in the encryption method. So the way it works is as follows. If Alice, a user, wants to encrypt a short message to Bob, let's say he wants to send money to Bob, Alice uses Bob's public key to encrypt the message, to send the money, and then Bob uses his private key to decrypt the message. Now this is for the case of Alice wants to send to Bob. If Alice wants to digitally sign a short message, Alice wants to authenticate himself to the users. Alice uses her private key to produce a signature, and then anyone who knows Alice's public key can verify that the signature could only be produced by someone who has and knows Alice's private key. So it means that there are two processes. The first one is public key asymmetric cryptography, and the second one is digital signature. Now, this is for between the nodes. What about the blocks? The blocks in the chain. The blocks in the chain are secure using secure hash algorithm, where the important property of these hashes is this. If one single bit of input data is changed, the output changes significantly, even if you changed a character from being small to become capital. The output will completely and drastically change, which makes it easy to detect small changes in large text files. That's why we call blockchain immutable. Nobody can manipulate it. Nobody can fake it or manipulate it. It's because of this feature. So this is brief, quick overview about and summary about the digital signature and asymmetric key used in cryptocurrency. For example, the transaction happens as follows. Using a digital signature, you have the transaction, whatever, from A to B. You have the private key, you create a digital signature. Digital signature with public key, you verify the transaction. This is coming from the sender that I trust, that I know that he's sending this transaction. So this is the digital signature. And one important note in the generation of keys and addresses. So originally you have your private key. The public key is generated from the private key, and the Bitcoin address is usually related to the public key, but it's generated using one-way hash function. So you cannot say that it's possible, but it's difficult to get back from Bitcoin address to public key because it's one-way hash function. As the name implies, it's easy to go from left to right, from public key to Bitcoin address, but it's very difficult to go backward from Bitcoin address to public key. But Bitcoin address is representing kind of public key, because public key, the meaning of public key is a key that anybody wants to talk to me should use it so that he can reach me. The same thing with Bitcoin address. Anybody wants to send money, he should use this address, which kind of resembling public key, but you cannot derive public key from Bitcoin address or with an efficient manner. It's usually difficult. Now the reverse process is very expensive, very complicated. Why? Because the mathematical functions that we use are easy to compute forward, but difficult to compute backward. Example of, like, let's give you a very difficult problem in math. Like if I tell you find the integration of e to power minus x squared, something like this, you cannot find the integration. There is no way on earth anybody, any mathematician, no matter how smart he is, no matter how intelligent that mathematician is, he cannot integrate e to power minus x squared dx. Can you please try this? So the encryption method, the function that it uses makes returning back is very difficult, just like integrating e to minus x squared. E to minus x squared, integrate this, you will not find any solution unless you do it numerically, and you will not find that. You will find just for certain values, but not for in general. So another thing, the public key is not the same as user's Bitcoin address. We mentioned this and told you although that Bitcoin address is generated from public key and it's related, but it's not the same. You cannot derive public key from Bitcoin because of that mathematical function difficulty that they created. So in summary, you have the signature algorithm and you have the cryptography public asymmetric encryption method, where you have the sender has something to send, whether it's money or text or voice or video or whatever, or password or data filled in a form. You have the public key to send to the user. The user uses the private key to decrypt. And this is asymmetric. The symmetric uses the same key at both the transmitter and receiver. So this is the key difference between them. And now let's look at the signature algorithm, DSA, digital signature algorithm. This algorithm is used also for authentication as well as confidentiality. And you have the signer has his data, then uses one-way hash function to get the hash. Then it goes through a signature algorithm using the signer private key, and then the output of this signature algorithm, you just send it to the verifier. The verifier use the public key, his public key, to verify that this data is coming from the original transmitter. So if we were to summarize them in a table, then we would say the following: that RSA is it's a crypto system algorithm, while DSA is a digital signature algorithm. RSA is used for secure data transmission. DSA is used for digital signature and verification, basically for authentication. RSA developed in 1977, DSA in 1991. It was developed by those people. The RSA stands for the first letter of the name of the inventors of the algorithm. R for Ron Rivest, Adi Shamir, and Laurent Adlama. And here DSA, for it was developed by National Institute of Standards and Technology, NIST. It uses RSA uses mathematical concept of factorization of product of two large primes. You just select two large primes and you try to factorize them. It's known this is a very difficult problem in math. In DSA, it uses modular expansion and discrete logarithm. RSA, it's very slow in key generation. DSA is faster a little bit compared to RSA. RSA is faster than DSA in encryption in general. DSA is slower. RSA is also slower in decryption. DSA is faster. And therefore, DSA, the main motivation behind DSA is the fact that it can make your encryption and decryption process faster. This is the main motivation behind this. So here are the main techniques that I want you to be aware of, and the ones that they are used in the standard. So all in all, although there are many encryption techniques and many methods, but the most common ones that exist on the internet are RSA, DSA, and the ECC. ECC is even used in cryptocurrency and Bitcoin. It's claimed by many scientists and security engineers that the RSA and ECC can be cracked using quantum computers with the help of Shor's algorithm. Now, this is fact that all these techniques can be encrypted. Unfortunately, it's a matter of computational power resource. When they say it's secure or you cannot decrypt it, they say this considering that the hacker is using a PC just like normal users. But if he uses a data center, a super powerful computer, then things will become faster. And he will be, if you were to crack something in 10 years, he will be able to crack it in 1 day. So it's a matter of producing powerful computers so that you can crack them. Okay. This is another homework here. I'm putting here in this slide. I forgot to talk about it. In this homework, I just remembered it when I read the statement that you can break these techniques. This homework teaches you how to break an RSA algorithm. Let's say you have a weak RSA algorithm. This homework gives you the Python code that you should write in order to break the encryption method of the RSA algorithm. So this, you can have a look at it as well and see what you can do with it. Because with examples, you can understand things better. Now, if this is true that these methods can be cracked and can be broken with the emergence of powerful supercomputers, quantum computers in the future using Shor's algorithm, then what are the solutions? What can we do about this? So the current solutions, researchers are thinking of the following possible solution. They are thinking of using not elliptic curve cryptography, something called lattice-based cryptography. Some are thinking of using hash-based cryptography, another type of cryptography. Some are thinking of using advanced encryption standard symmetric cryptography with one secret key shared between two nodes securely, and this key has length close to the length of the message itself. Some are talking about quantum cryptography. Some are talking about physical layer security. So what the researchers right now and scientists are looking forward, they know for sure that those encryption methods that are currently being used in the internet are not robust enough and they can be hacked and we cannot rely on them. They are not reliable. And they are thinking of other approaches, other alternatives. And one of these alternatives, one of the strongest actually, is the physical layer security concept. Because the first three concepts are related to the math, to the complexity approach. They try to make the algorithm much more complex, that's it. And whenever you come up with a super powerful computer, you will be able to hack the algorithm and crack it. And this quantum cryptography, the main problem with the quantum cryptography that you need still to share a key, and to share a key you need to have trust party, and this key, the length of this key is really huge, and you need to have a secure channel and secure method that can make sure that only the legitimate receiver can get it, which can cause significant signaling overhead in the network and can reduce the throughput and can make the network really very, very congested. Now, the strongest one remains to be the physical layer security approach, which is this. This is expected to be the most significant one. And the reason for that is because this approach can help you achieve perfect secrecy, which means zero information leakage to the eavesdropper without even sharing a key between the transmitter and receiver. This is the beauty of this approach. So when we say we don't need to share a key between the transmitter and receiver, this means that you don't have signaling overhead, you don't have throughput reduction in the network, you don't have congestion, you don't have a third-party trusted node to distribute the keys between the nodes. On the other hand, you won't need to have complex mathematical functions like elliptic, lattice, hash, and those complex functions in order to generate your encryption method, to generate an encrypted message. And in addition, it can be coexisted with the low complexity devices that require light encryption. There is this conflict in low complexity devices that they want security to be high. They want to be having ultimate security, but the problem that those devices cannot afford consuming too much resources and power and latency and battery to encrypt using asymmetric encryption methods, for example, RSA methods that consume too much power, causes latency and delay to the network, and can consume the resources of a low complexity device like Internet of Things very quickly. So it makes it less efficient. Although people are saying that we should be using those methods, we should reduce the encryption complexity at the Internet of Things device to make the battery last longer. But the problem when you do this, the security level gets compromised, and we don't want this to happen. Now, for those of you who are asking, can quantum computers hack Bitcoin? I recommend you to watch this link video here so that you learn more about it. Although there is a bias in the video a little bit, because eventually we will reach to a point where cryptography should update their security algorithm to a much more advanced one, and hopefully ones that don't depend on math complexity. So I think we can stop here now and complete after 10-15 minutes. So thank you everybody, and we can continue after 10 to 15 minutes. Thank you.